Hi everyone, this is Aman again, and I'm here with a walkthrough video for the CSE 331 project about problem 4. In this video, we'll give a brief overview of problem 4 and go over a valid solution. Let's start by giving some context to this problem. As discussed in the earlier walkthrough videos, we focus on a portion of the lawsuit filed by the New York Attorney General against Spectrum. So Spectrum had a customer base that did not have an option to switch. That is, there were few choices for the subscribers. As a result, the New York Attorney General alleged that Spectrum took advantage of the fact that it was effectively a monopoly in these areas and did not provide reliable internet service to its customers. Continuing with the monopoly theme, this problem has for-profit only as a monopoly in rural areas. The clients in these rural areas are placed in set R, which is a subset of the set of clients C. What differentiates these clients from the other clients is that they have infinite tolerance threshold alpha C, that is, they cannot unsubscribe from for-profit only services, even if the internet service is below par. However, they can still complain. Remember that the clients in R have infinite tolerance threshold due to the fact that they have no other option to switch to. Now let's examine the inputs to this problem. From problem 3, we add two things. One is again the set of rural clients R and C, and the other one is having these clients' tolerance threshold alpha C set to infinity. As in problem 3, we start with the graph G equals V comma E with V as vertices representing the clients and other routers and E representing the edges between them. There's always the content provider node 0 denoted by I and the set of clients C and V complement I. Regarding the bandwidth values, the bandwidth value B sub U for all routers U and V is less than infinity. That is, it can be any non-negative integer. Again, we have the tolerance threshold alpha C and also the complaint threshold beta C for all clients C. Here both numbers are going to be greater than or equal to 1 for all clients. We also take out a subset S of client C that is later used to calculate penalties. You have the row lawsuit value as well. If this fraction of clients complain, then that results in a lawsuit for profit only. We also have the row FCC value, and if this fraction of clients in S complain, then that results in fines from the FCC. Regarding the lawsuit and the FCC, we also have the fine amounts. $8 is the lawsuit settlement amount and $B is the FCC fine amount. Now we've added the set of rural clients R, and for these clients in R, the tolerance threshold alpha C is equal to infinity. Finally, we have the initial priority value for all clients in C equal to priority default, which is 0. And it would cost $Z to increase bandwidth by 1. Again, the difference in inputs from problem 3 is highlighted here. Now let's go over the outputs. We want you to output three things. A list of paths speed as of C for all clients that is going to be used by the routing simulator to route packets to each client. Also a list of priority values, priority of C for all clients. Remember that you can change the numbers from priority defaults for each client, and that the routing simulator can use this to prioritize while transmitting packets in case of bandwidth limitation. So please be mindful of this fact while designing your solutions. And a list of bandwidth values B sub U for all routers U. You can change these numbers, but it's going to cost you $Z for each unit change. The objective here is, as always, for your group to maximize total revenue for profit only. The penalties are defined in the same way as in problem 3. That is, we have two penalties, pen not and pen 1. Pen not is the same from problem 1. Pen 1 is defined informally by incorporating the fines from FCC and the lawsuit. Also, we take care of the subset of clients that the FCC and the AZ keep an eye on. Informally, we have the definition of when a client complains and what it means if at least row times T clients complain. And we have the following parameters for defining pen 1. So we have the following definition for pen 1. First, we have the definition of a client complaining and the definition of pen 1. Case 1 is for the lawsuit and case 2 is for the FCC. Also remember that both can happen or neither. The revenue from each client remains the same with the penalty amount pen not taken care of here, but the total revenue is redefined by adding the revenue amount and also subtracting any fines or costs of bandwidth increases. Again, both cases are considered separately and together. Now that we're done recapping penalty revenue definitions, let's go over a valid solution for problem 4. As always, we have the table on the top right corner with clients, their current locations, and the yet to be determined routing delays. We also have the path key table just below that and the minimum path delay table after that. Let's take a look at the priority table here. Remember, you can change the priority values, we just haven't done so for this solution, and this also holds for the bandwidth values. Also, we have highlighted clients 3 and 6 with a dark blue background as the subset of clients for the FCC calculation, and client 8 as the only client in R, the set of rural clients. Finally, let's go through the paths for clients here. As you can see, this solution is different from the other solutions. Take for instance the path for client 8, PDAS of 8. Previously in problem 3, the path went from node 0 to node 9 to node 3 to node 8. Whereas in this solution, it goes from node 0 to 10 to node 1, then to node 5, and then finally to node 8. So now let's start with time tick 0, and all the packets are at node 0. And since the bandwidth value b sub 0 is 8, greater than 5, the number of packets to be transmitted, the packets are forwarded to their next location, and we proceed to the next time tick. Here, the packets have followed their respective paths and the table has also been updated. Again, if you look at node 10, then it has bandwidth value equal to 7. So for node 10, that is bigger than 4, the number of packets to be transmitted. And at node 9, the bandwidth value is 1, and there is only one packet to be transmitted. So we move to the next iteration without any delays. Here we're at time tick 2, and the packets for all the clients have followed their respective paths again. Let's now focus on the packet for client 1. The packet is at node 1, which is its destination, and this is reflected by its current position being updated to 1. Here, as in all the other iterations, the simulator checks if a packet has reached its destination, and since the packet for client 1 has, the routing delay for client 1 is set to the current time tick, which is 2. We again see that the bandwidth value b sub 1 is 7, greater than 3, the number of packets to be transmitted. Remember, packet 1 is already at its destination. And at the other end, node 3 has bandwidth value b sub 3 equal to 1, and fortunately only one packet to transmit, so we proceed to the next iteration. At time tick 3, we look at nodes 2, 4, 5, and 6. For nodes 2, 4, and 5, the bandwidth values are 4, 2, and 4, all greater than 1, the number of packets to be transmitted at each node. So the packets will be forwarded along their respective paths. At node 6, however, the packet for client 6 has just reached its destination, so the routing delay is set accordingly to 3. At time tick 4, we see that the packets for clients 3, 6, and 8 have all reached their destinations, so the routing delays for each client is equal to 4. Now let's go over the penalty revenue calculation resulting from that solution. Here we have a table with headers, client C, their minimum path delays, little d of C, the routing delays, capital D P dash of C, the tolerance threshold alpha C, the tolerance threshold alpha C times the minimum path delay, little d of C, the predicate for the penalty definition, whether capital D P dash of C is greater than alpha C times little d of C, the penalty amount pen naught, the complaint threshold beta C, the complaint threshold times the minimum path delay, little d of C, and whether a client complains or not. We also have the pen naught definition below the table. Let's start again with client 1. The minimum path delay for client 1, little d of 1, is equal to 2. And as we saw on the last slide, the routing delay, capital D P dash of 1, also equals 2. The tolerance threshold alpha C is equal to 1. So the product of the tolerance threshold times the minimum path delay is equal to 2. And the predicate for examining penalties, whether the routing delay dp dash of C is greater than the tolerance threshold alpha C times the minimum path delay little d of C, is false, since they're actually equal. And as we see from the definition below, the penalty for client 1 pen naught is equal to 0. Now the complaint threshold for client 1 beta 1 is 1, and thus the complaint threshold times the minimum path delay is equal to 2. Now we move to examining whether client 1 complains. Remember that the client complains if the routing delay capital D P dash of C is greater than beta C times little d of C. In the case of client 1, they're actually equal, so client 1 does not complain. Similarly, for all the clients, we have the following values. For a second, let's focus on client 8. The routing delay for client 8 is equal to 4, but the product, beta C times little d of C, is 3, so client 8 actually complains. Now let's calculate the revenues for each client C, with the table here as well with headers. Client C, their penalty amounts and their revenue amounts. Below that, we have the definition for revenue, which is basically payment minus penalty pen naught. From the last slide, we know that the penalty amounts for each client equals 0. So the revenue amount for each client equals the full payment amount, payment of C. Now we calculate total revenue. We have a table here as well with headers client C, the payment amount, payment of C, the revenue amount rev, and whether the client complains or not. So let's start by going over the fines if there are any. For the FCC, the set S includes clients 3 and 6, and since none of the clients in S complained, that means 0 complaints for the FCC. For the Attorney General lawsuit, the set S is the entire set C, and since client 8 complained, we have 1 complaint for the lawsuit. Recall that the row values for the FCC and the lawsuit. And we see that the fraction of clients that complained for the FCC equals 0, less than 0.5, so no fines from the FCC. Likewise, for the lawsuit, only 1 client complained, and so the fraction of clients complaining is 0.2, which is still less than 0.4, and hence no lawsuit. Here we have the definition for penalty pen 1, and since the fraction of clients complaining didn't exceed the given constraints in both cases, the penalty amount pen 1 is equal to 0. Finally, we have the definition for total revenue for both cases, and since we did not increase any bandwidth values, x times z is also 0. And as discussed, pen 1s are 0 for lawsuit and FCC. So we have the following total revenue formula. So we have the same table from the previous slide and the total revenue formula as well. And we have the total revenue amount equal to $190. This is by adding the revenue amount from each client, which is payment amount for each client. And again, this is the maximum possible total revenue amount. Now we'll apply the solution for problem 3 to this problem. So the paths are shown on the graph and the bandwidth values are increased for client 3 and node 9. The routing delays resulting from these paths are highlighted with an orange rectangle in the top right table. For a more detailed run of the simulation, please go check out the project webpage. Using those routing delays, we do the required computations to get the following. Here, client 8 does not complain. The revenues from each client are also the same as in example 4. The penalty amount is 0 for each client, and thus the revenue is also equal to the payment amount. Now we calculate total revenue. For pen 1, we see that no one complains and hence there will be no fines. Finally, we have pen 1 equal to 0, and the total revenue is calculating using this formula. However, this time we increase the bandwidth by 2, but the fines are still 0. Thus we have the following formula for total revenue. Now total revenue equals $160, where we add the payment amount from each client and then subtract the bandwidth increase cost. This is of course less than the revenue from example 4. As always, if you have trouble understanding any part of this video, then you are more than welcome to post on Piazza. Thank you for watching.